Hello everyone, I am Seunghan from Inha University. I am honored to be able to present here. My presentation topic is design and performance test of a newly developed 10 micron aerosol 3D printing nodule system for EMI shielding and semiconductor interconnect. Here are the contents of the presentation. I will start with research and background and purpose, design and fabrication of a pneumatic aerosol 3D printing dispenser for the semiconductor and performance test. At the end, I am finished up with a conclusion and future research directions. As semiconductor 2.5D packaging and chiplet technology advance, the semiconductor market demands new printing technologies to address the challenge of the fine pattern implementation and the structural constraint. Unlike the traditional inkjet printers with 100 micron precision, there is an increasing demands and academic research for aerosol 3D printers and metal ink that can achieve finer patterns and print on three-dimensional planes, offering greater precision than 100 micron semiconductor dispensers. In this study, we have designed and developed an aerosol 3D printing systems capable of printing with 10 micron precision on three-dimensional planes. We have also evaluated its process performance and are presenting domestically produced equipment applicable to semiconductor processes. Inkjet printing has a low viscosity of less than 12 cp with continuous drops of 30 micron and standoff distance of 1 millimeters. In contrast, aerosol 3D printing allows for 3D printing with a standoff distance of over 5 millimeters. Continuous streams of 1 to 5 microns drops and can handle viscosities up to 1000 cp dispensing technology. On the other hand, produce line width of around 100 microns with non-continuous drops and high viscosity printing capability aerosol technology, which enables 3D printing and achieve 10 micron precision, was developed due to these advantages. Overseas companies like Optomek and IDS Nanojet are selling such systems, but they are expensive and not yet applied to semiconductor field, prompting the development of this technology. The developed equipment can be applied to semiconductor packaging. A representative example is used for electrostatic shielding. Previously, metal cap was used for static electricity shielding, but as circuits are becoming more precise, direct printing is now being used. The picture in the SIP of Apple mobile phone 1 in the picture, an example of a bond chip is printing directly into trench instead of inserting the existing cap or metal directly. However, due to the current line width being small, aerosol is used instead of dispensing. You can see an example of trench and peel in the picture below. The Fraunhofer Institute has been working on 3D packaging as a replacement for wire bonding, and the IMEC Institute has implemented 2.5D packaging in photonic chip. The Fraunhofer Institute has implemented a three-layer RDL as an aerosol. The scope of research is equipment development and process development. The equipment is A3DP nozzle development, 3-axis system development, integrated system software development, and G-code-based system and semiconductor packaging dispensing system development. The process development suitable for this device was conducted and verification was conducted. The final goal is to develop equipment and process for semiconductor applications. The developed equipment for each system is shown on the slide. The final goal is to supply an aerosol 3D printing dispenser with a 10-micron line width that can be used in semiconductor production site. On the right, you can see the final implemented equipment and the 10-micron line width. We designed and precision machined the 100-micron nozzle on the left and conducted the design experiment in two ways. All parts are 100% domestically produced. We also designed the control system directly from the manual control and developed the PC-based control system programs. It is designed pneumatically. MFC control is PC-based, and the software has been developed to connect a camera in real time to measure the line width and to control the line width. Additionally, we have developed a system that allows temperature control of the atomizer with ink and the substrate to be printed up to 300 degrees, enabling summer sintering simultaneously. We also developed a G-code-based system so that it can be used in the same way as an existing competitors. In addition, we used to dispensing authoring tools of the semiconductor dispenser so that it can be used intuitively and can be used in the semiconductor manufacturing environment as before without additional training. We developed and installed a pneumatic shutter, and the specifications are the same as those of the existing dispenser. As the aerosol nozzle is installed on the dispenser used in semiconductor field, the dispensing speed and size are same as those that can be used directly in the semiconductor processes. The product on the right is final product, and the dispenser that links software and hardware is a product of Nanojet Korea. It can be used directly in the semiconductor packaging production field. Materials and ink. Nanoparticle ink and conductive polymer PEDOT were used, and the EG was added to them to enhance the resistivity. These are the specification for each ink. This is the experimental method to measure the exacted line width. A Keyence VHX E250 E2050 model microscope was used. The VHX E2500 microscope support 4K and can observe and collect data at magnification of 20 to 2500 times. The VHX E2500 equipment provides 3D data on the height and the shape of surface, so that data can be secured up to the microstructure. The circuit resistance was measured using a high resolution source meter, precise resolution source meter, K3 2634B. The figure on the left measures the change in status with respect to the standoff distance. In the case of inkjet printing, the standoff distance is 1 mm. In the case of aerosol 3D printing, it is regulated to be within 5 mm. In this experiment, a specimen was made with PSS ink, and the line width was observed from 1 mm to 8 mm using a high magnification microscope, and the line distortion phenomenon was confirmed at the standoff 7-8 mm. The figure on the right measures the change of line width by the printing speed. It was confirmed that the printing speed of the aerosol 3D printer has an effect on the line width and thickness. The left picture is an experiment on the thickness change by repeated ejections. Repeated ejection of the aerosol 3D printers printing affects the change in the line, the thickness. The right picture is an experiment on the line width change by cess gas. As a result of observing the change in the line width by increasing flow rate of cess gas from 10 SCCM to 12 steps, it was confirmed that line width control is possible by cess gas. We conducted an experiment to find the usable line width section by controlling FR, shape gas, and atomized flow, and also found a method to control the side view. The FR value is ratio of the flow rate and aerosol entering the nozzle and the flow rate of cess gas. As a result of the experiment with the FR value, we able to confirm the change in the discharge quality according to the FR ratio. The experimental results confirmed that the printer quality was good at FR5 and 6. The printed circuit was sintered in electrical furnace at 200 Celsius for 10 minutes, 1 hour, and 2 hours respectively. The left is the experimental result of Fraunhofer Institute. Upper right is a picture measuring the shape and lines of sintered line. In the picture A, you can see the particles before sintering, and in B, you can see the sintering particles. The picture on the right show that our experimental result has particle size similar to that of a picture on the left. To observe the cross-section of the circuit, the specimens were processed using an iron milling system's IMS Hitachi Ablade 5000, and the microstructural analysis was performed using a field emission scanning electron microscope FESEM JSM 7100F to analyze the sintered morphology according to the printing and sintering conditions. Similar results to those of previous paper were obtained. We conducted tests on the nozzle of 100, 200, and 300 microns, and the result of ejection using a 100 micrometer nozzle were 11.27 and 15.89 micrometers, which are close to the minimum line width of 10 micron. In the figure on the right, we found that the phenomenon of clouding due to overspray occurred not only in Ina University's machine, but also in the machines of other companies. As a result of conducting a fluid analysis on the phenomenon of overspray clouding during the experiment using the ANSYS programs, the pro-clouding phenomenon was confirmed in the nozzle part, and it was confirmed that the ejection quality was affected depending on the structure of nozzles. Therefore, we plan to find the solution and process a new nozzle for an experiment. The conclusion is as follows. We developed equipment that can be used directly in the semiconductor dispensing process, verified its performance, and implement a line width of up to 10 micron. It can be used directly in production by replacing the A3DP nozzles in semiconductor production facility or installing the new equipment. Future research directions are below. Study on the improvement of turbulent flow phenomenon through nozzle 3D fluid dynamics. Study on design and installation of laser hardening device for intermediately sintering. The study installation of AI-based program in FR control system. Study on the replacement of wire bonding. Study on solving the shielding problems of sputtering and spraying method. Study on the process stabilization through metallurgical characteristics analysis. Thank you for listening my presentation.